Sounds pretty wavy. And welcome back. Hope you had a good break. Just 5 more weeks, and physics will be part of your life forever. By the way, that's the music of the famous Russian Rimsky-Korsakov. Korsakov, I think that's how it's spelled. Scheherazade, very wonderful piece. Scheherazade, something like that. Okay, and what I wanted to, first of all, any questions about anything? I did put some notes up on our B course about the content of the final, what's going to be excluded. Not very much, really, but a few things are not going to be covered, and a few things extra will be covered. For example, our discussion of different kinds of magnetic materials was a little bit more inclusive than the book had. So you should know diamagnets, paramagnets, ferromagnets. The book covers diamagnets a little bit. You should know how they work. Paramagnets he doesn't mention at all for some reason. I don't know why. It's something you all use because nuclear magnetism is paramagnetism, and ferromagnetism he does mention also. But you want to see the whole picture, I think, and its similarity to the electrical case where we have again the same sort of thing with some variations. So we have the dielectrics, paraelectrics, ferroelectrics. So, good. If there's any question about that, bring it up. Today, I wanted to go a little bit more over optical instruments, just sort of clear it up. And I came across this very nice simulation, which I commend to you, it's actually started out at Davidson University, but I think the best version is actually on a website from Boston University. Can you see the URL up here? Where's my arrow? Yeah. physicsbu.edu optics. If you just Google that, you'll find this thing. What's nice about it, it allows you to bring in more than one optical element, namely lenses and mirrors, for example. Lenses or mirrors, you can just call them up. You can adjust I can turn off the object, I think. Oh, I put in another object. Oh, what I have to do is, you can clear the object by clear the active object. If I make it active, I can clear it. For example, I want to clear all my objects, for example. Let's try and do it again. So it's quite nice. What it does, if you make this active, it shows you the focal distances. So here it's a positive focus, it's a converging lens. If I move the focus through the center, I change it into a diverging lens. Isn't that nice? It's very sweet. I can go from one to the other. I can change its focal length. Notice the focal length gets larger. This is this thing here. As I go further away, it gets flatter. And as I make it shorter focal length, it gets rounder. This is what you expect. Can also make mirrors here. If I activate this one, I can make this looks like a diverging or convex lens. If I put the focal length through the center, I can make a concave lens. So I can construct various things that I want. 2 lenses, 2 mirrors, etc. I think you'd even put 3 and so on if you wanted. And it's very nice. And I'd like to quickly go over, just to systematize. I tried to do it the last time, but I think I could do it again with this demo, this animation rather better. Let me, for example, get rid of this one, clear it, and move the lens here. Make the focal length about so. So here's F. So 2F would be about here. They don't show 2F. But it turns out 2F is a very important point. Because if your object is, now let's put in an object, say out here. Okay, and let me make it a little taller. Okay, nice. And here are the principal rays of that object, the one that's going parallel, and it goes through the focal point. The focal point was over here, creates a focus over here where the image is formed. And the point is that I can't see the, let's raise up the focal points again. You see how the light passes through it? And here's the other one, and we're outside of 2F. Now, what counts for both lenses and mirrors, as I point out to you, they really behave in very similar ways. As I bring the object toward 2F, at first the image is real, the light passes through that point. So I put a screen here, I actually get an image, and the light passes through it, just as though this were a real arrow over here. Light is coming out of it, just like it's coming out of here. And the things seem to seesaw around 2F. That's the interesting point I wanted to make. So 2F is, let's check it again. 2F is about here. So let's say I approach, let me move, let me move it over here a little bit. Because I want to have room over here to do it. So F is here, 2F is about here. Let me bring the arrow in, collect it. And as I bring it in, at 2F, what happens is the arrows become of equal height and opposite in sign. It's just about 2F here. So at 2F is the place where the object and the image have the same height. The magnification is 1 at 2F. If you're outside of 2F, you reduce. When you reach 2F, you're the same. If you come inside of 2F, you magnify. So that's the picture. And so let's just see that to be true. Here, if I'm bringing it closer to 2F, I'm saying that the image will move out. It gets further away, and between F and 2F, you see how the image is enlarged. So that's the pattern until you get to F. Let's see where F is again. F is here. Okay, so now if I get to F, now at F, the image gets to be virtual. You see how the rays are diverging here? As if my eye were here, it would see a virtual image over here. So the pattern is that when you go, just like you to see the whole picture. If here's your image, your lens, which sometimes we just simply signify by that top part because you don't want to take up too much. So that's a converging lens, right? And if you have F and F and 2F and 2F, if you're outside of 2F, then you get, in this region, the image will be reduced of real and inverted. Inverted. That's when you're beyond 2F. This, though, is my object at this point. Then if you're between 2F and F, the image is now enlarged. No, right at 2F, then the image is sort of, the height is equal to the height of the object. So the magnification is 1. Or actually -1. So the image heights are the same, just at 2F. That's the crossover point. That's what's so nice about this. This is the crossover point where they're equal, and inside of here, you have that the image is, again, real, but it's enlarged, and, again, inverted in this region here. And in this region here, the image is virtual, enlarged, and it's upright. This is the upright. This is the shaving mirror or the cosmetic mirror region. Well, if this were a mirror. So that's true of lenses. Now, it's also true entirely with mirrors. Oh, well, let's see, just for fun, we could change the focal length to negative and see that at all distances, this thing is diverging. But actually, we'll see in a second that even though it's diverging, you can sometimes use it to make an image. But you see, here's the object. The image is this little guy down here where the rays seem to be coming from. So if your eye were here, it would see the image over here. But regardless of, let's see where the focal points of this thing is. Oh, okay. So let me even make the focals a little bit more visible. So here's F and here's 2F, but it doesn't really matter with this thing because wherever it is, the image is virtual, and however I bring it, the image doesn't seem to do much different. It stays virtual and reduced. So this is your diverging lens. You see, it's pretty much the same everywhere. Okay? So there's the systematics of it. Now, for example, I could get rid of this thing and put in a mirror, say over here someplace. Okay, now here's a converging mirror. Why do I have an object already? Let me get rid of this object, put in. Oh, okay, it's okay. Yeah, so here's an object, and let's get the focal length of that mirror. It's about here. And it's a concave mirror, so it's a sort of a converging type of object. And let's make its F a little bit bigger. So its 2F is about here someplace. So when I'm outside of 2F, again, my image is real, inverted, and reduced. Outside of 2F, the image reduced, real, inverted. Now I'm talking about mirrors. But it's the same story. That's the nice thing. And if I bring the object within 2F, no, 2F is over here, F is here, 2F is about here. So, okay. So let's look what happens to as I bring it closer, at 2F, the two are in the same place and equal in height. Just like with lenses. At 2F, the heights are the same, the inverted, at exactly 2F. This is actually what we did. If you remember the little demo with the bouquet, this is what the bouquet story was. What we did, we hung some false flowers upside down over here, and what we did was create, this was the, it was the upside down. See, this was the object was upside down. But what we did was create an image. Think of this upside down now. The bouquet was upside down, so the bouquet was hanging here. There was a concave mirror. The light was reflected, created an image where the light went out. When you stood over there, it looked like the light was coming from here, and it looked like the flowers were upright. You see what I'm saying? It was sort of the opposite of this particular. I don't know if I can turn that. Oh yeah, I can. Okay, so this is what we did. Yeah. Oh, this is very nice. Yeah. Yeah. So the bouquet was hanging upside down like this, as you saw when you're on the way out. The light came up. It created a real image over here. You stood over here, and it looked to you like the flowers were over here, when in fact they were upside down over here. That's exactly that demo. And there was at the 2F. It was at 2F. And so the image was exactly the same height, but just inverted, and it looked real. So do you see that now, how that optical illusion was created. Okay, so, well, let's stick with this if we like. Well, all right, yeah, why not get used to looking things upside down? So if you go between 2f and f, what happens is that the image gets larger. So you're getting into the region between 2f and f, where the image is enlarged and real between 2f and f. This region in here, 2f and f. If you're in here, you get this enlargement. Now, so this is, again, exactly what you get with the lenses when you're between f and 2f. And here, now this is the shaving mirror or cosmetic mirror image. Between f and the mirror, you get divergent light. You get your inverted image as though the light were coming out of there. And it looks enlarged. It's further away from the mirror than your object, and it's enlarged, and it's the same height. It's the same direction as the original object, right? I mean, I have the arrow going upside down, but the image is also upside down. So you get the same situation. It's virtual, enlarged, and the same direction, that is to say, upright with respect to the original object. Now, the other point that I would make from all of this is that there are two situations where you get enlargement. And often that is the case that you want, like you want a microscope or a telescope where you're trying to see something that's small or far away and you're trying to see it better. So those are the cases you would be particularly interested in. You want to put your object not out here, but either between 2f and f or inside of f in order to get enlargement. So that's what you're going to run into when you start studying magnifying glasses, telescopes, and microscopes. They all have the feature that you are dealing with things in close. Actually, it turns out that you want to be close to the focal point. Let me show you why. Let's look at the formula for. Again, I'm running. Oh, there's my white chalk. I'm just trying to do something simple here. Let's just look at the formula. Yes, sir.
So at F,
Yeah.
Yeah, is it inverted or
Oh, hell breaks loose at F. Well, let's try it. Let's see what happens. Just at F. It's really disaster. See, it's changing between real and imaginary. So you get an image at infinity, and you'll see the curves when you plot that. It goes to infinity. So you don't want to be right at F. But let's just for fun. You can play with this yourself with this animation. Let's remind ourselves where F is. F is over here. Okay. So let me go right toward it. Look what happens right here. So all kinds of crazy things happen. Look at switching. Look at this line here. It just jumps from going up to going down in a flick. So that's kind of a tough place right there at F. So you want to be. I think the idea is you want to be either here. Now here it's reasonable, because you see the light. It looks like it's diverging from here. So at least you got something. You see, at least you got something cooking here. Or if you're on the other side, you got something. You see, your image is over here, but right at F, it's a blur. So we'll just stay away from that. Okay. But you want to be close, and that's what I wanted to show you now, because I don't know why the books don't say this very simply. Remember that the definition of magnification is minus the image distance over the object distance, right? But the formula is, of course, we have our familiar 1 plus s plus 1 over s prime equals 1 over f. And by the way, this kind of shows you the symmetry between s and s prime. If you switch s to s prime, nothing really changes. So that's why you get this swinging effect when one is enlarging, the other is reducing, and when one is reducing, the other is enlarging. You get this swinging effect, and the swing occurs when s is at 2f. But that's a whole other story. But from this formula, you can get, for example, s prime. You can solve for s prime, as I showed you before, by this other formula, s minus f, right? That's just the right side up version of s prime. Okay, so let's now put that in this formula. Let's put s prime is sf over, well, s minus f. I'm going to write it that way. So this is s prime, right? I've just put a bracket in a peculiar way because I want to isolate s. That's this s. And here you have the s from here. So they cancel, and you get that the magnification is just f over s minus f. Now, isn't that interesting? If you want to get a large magnification, you want to divide by a small number. So to get large magnification, you want s to be close to f, because then s, especially if they're the same sign, because when you one will almost cancel the other. You get a small number on the bottom, and you get a big magnification. So that's what you'll see, all these people that work with telescopes and so on, microscopes. If you want large magnification, you put the object close to the focal point. And when you study these things, keep that in mind. That's the trick they're playing. They're just trying to keep the object close to the focal point. And that's why. Especially when S and F have the same sign. So in fact, you could have a negative focal, if you have a negative focal object, like a diverging lens, what you want to do to get a large magnification, you'd have to put the S negative, which means that the object or the image has to be behind the lens. That's a certain type of telescope, actually, which uses the feature that even though you have a negative focal length, you can get magnification if you make the object behind the lens. This is actually my friend Galileo, I'd like to think of him as my friend. He's thought of that, actually, in 1600. And he made a telescope where he uses a negative lens, but he puts the object behind the lens near the focal point, and he could get good magnification. So he made a terrestrial telescope like you see the spyglass of Captain Blood or Captain Hood, looking out through the telescope. That's a Galilean telescope where he has a negative lens. I think I can show you that. Do we have... I wanted to get onto diffraction, but let me at least show you the Galilean telescope, because it's so clever, and he must have been a very smart guy. He dreamed this up. So what he does, let me get rid of this mirror. Let me put in two lenses. One is this one. Let me make it with a long focal length. And let me put in a second lens, as Galileo would, here. But I'm going to make it into a negative lens, so you think, oh my God, trouble. Yeah, but I'll make it a short focal length. Okay, now let me for the sake of familiarity, make the arrow upright. And now what I'm going to do is put the object, now this is supposed to be a telescope, so it's looking at an object very far away. It could be a person, could be a ship, could be a star, but it's far away. So let me put it way back here. Okay, now let me move this, perhaps. Yeah, so here's my story. You see, well, this is not very good because I'm inside the focal length. I want to make this very far away so that's actually reduced. So what this first lens is doing for me is just collecting the light. It's not magnifying, so it's not doing me really very much good because, you see, the image is actually smaller. I wonder if I can make this better. Yeah. So here's 2F. So this thing is reducing. It's difficult getting all of this on the one page here. That's the problem. All right, now we definitely see that this is a inverted, reduced image. Now I have my other lens here, which way out here isn't doing me terribly much good. You see it's diverging and it's creating, again, a reduced image. But Galileo figured out that if I put this close to where this, see now this is now the object for this lens. And the trick is put the object near the focal length of this next element. But in the case of a diverging element, I should put it on the negative side. Wow, you see that? See, I put it on the negative side, and look where the image of the second image is. It's already enlarged. And if I go even further, I get an erect virtual image, right side up, enlarged. So Galileo has made us what we call a terrestrial telescope. In other words, for looking at far distant things, if you put the negative lens, let me see where its focal distance is. See, it's a short focal length, and I'm putting it near the object. And look how giant I can make it, so much so it's off scale here. See, if it's near the object, it's near where the focus of this first lens is. So the object for this lens is over here. It's behind the lens. And when I'm close to that, I get this giant magnification. That's clever. Look, I don't want to spend too much time. I'm just showing you where it is. You can play with this at your leisure. You can do the math. You can actually put in all this thing, but you have to remember that if this lens creates an image over here, this is now the object for this lens, which is over here, and that object is at a negative object distance from this lens because it's behind it. And then you want to put that object close to the focal point of the second lens, either before or after, and you'll get real or inverted images. And it's really pretty much contained in this idea here. Okay, so that's a collective idea that will help you, I think. All right? Think about it. Just write it down for now. I don't think it's in the book, but I think it's worth doing. And I think it also helps explain all the different optical instruments that you'll be faced with, both magnifying glasses. Again, you put the object very close to the focal point. The microscope. The microscope works by a similar thing where you change. You have two lenses, and what you do is, in that case, you put the focal length right close to the object. This is the objective lens, and you put, I want this to be a positive lens. that has, so you have magnification there, maybe too much. Mm-hmm. All right, yeah. And then I want to have, let's see where this one's focal lengths are too much. Let me make it a little bigger. And what you do is you bring this eyepiece close again to, this is now the object, and here's the focal length. So you bring the object distance close to the focal length, and you get this enormous magnification. See what this thing is going way up here? So it's almost too much. See? So if you bring the focal length of the second thing near the object distance, you get magnification. In this case, it looks like a virtual image. If I go on the other side, I get a real image. See the real image here? This is the real image of the second one, but I can make it large by bringing the object, the focal length near the real object. So this is a microscope. It's an eyepiece here, and an objective lens here. And again, I'm using the trick that the object is near the focal length so that I get magnification in the first stage, and then I get even more magnification by putting in a second stage. And again, the object, which is now the previous image, is close to the focal length of the second thing, and I can get real and virtual images of that. So that's your microscope. So you've seen a telescope, far distance. So, but I think they're always the unifying features that they're using the same trick as being close to the focal length. Just the objects being close to the focal length gives you magnification. I hope that helps a little bit. I'm just trying to bring some unifying ideas to this story. And, okay, let me put it away. And the other, now I want to switch over to the next chapter because we have to keep moving, unfortunately, although there's much interesting stuff here. To interference and diffraction, chapter 32. Okay. Now, there are a lot of interesting applets to illustrate this because it's a kind of graphic thing. Oh, the other feature that we're getting changing is that all of this, we treated the light as a ray, and we just indicated the direction that it was traveling. Now, in this chapter, we're going back to the fact that light is a wave, and that it has the properties of, in particular, wavelength is the important feature here. Some things depend on wavelength, some things depend on frequency. We'll sort of straighten that story out too. But the outline of this chapter is we have to understand the idea of waves interfering. Do you remember this from 8A? Did you have this in 8A, interference of waves? One head shaking, yes. Okay, I don't have to spend too much time on that. Then the other feature is diffraction. Did you have that in the other section? Do you remember? Does that ring a bell? Diffraction. Well, here, what we're going to invoke is Huygens' principle, the idea that a wave propagates by sending out little wavelets. We use that to understand reflection and refraction because we said a new wavefront was formed by these little wavelets. But the interesting thing about that is that if you come to an aperture, or let's say you have a wave coming in around Santa Cruz's pier, you can't exactly hide it entirely behind the pier. The wave seems to bend around and go around the pilings of the pier. So that's the diffraction effect. And that comes from the concept of Huygens explains that. Again, I'm running into my machine switching when I don't want to switch. So we'll get diffraction. That's sort of the bending of waves. And then what the idea is that if you can get, say, 2 slits, or even one, you get the waves coming through these slits and they bend out, they can cross over each other, and then you get the interference effect between the waves coming from the 2 slits. So this is a very powerful effect, and it's used to determine the wavelength of light, for example. And that's a very important concept of the wavelength. So we're going to have diffraction of waves, and then the waves will interfere. For example, 2 slits, where you can have many slits. You can have the periodic atoms, say in a crystal or in a molecule, say in DNA. The structure of DNA was discovered by doing diffraction off of good old Rosalind Franklin did diffraction off of DNA to get its structure, which, of course, is a tremendous result. Then you can even get from one single slit, you can get diffraction from different parts of the slit, because waves coming out from every part of the slit. So we'll see one slit, and then all kinds of things like this. And the other thing that they don't talk about much in the book, but I think is important, is how you actually see light by the scattering of light, and why the sky is blue. So the next story is, again, I want to make this pretty general in that it's just another of the properties of light, of waves, not just light. Diffraction, interference are general properties, all waves show them. The other thing I never did mention when we talked about polarization only occurs for transverse waves, because we had the idea that you have like a molecule and the wave is going like this and sending electrons up and down the molecule, or it's this way and it doesn't. For a longitudinal wave or a compressional wave, that isn't true. For sound, you don't have polarization. I should have mentioned that, but let me mention it here. So we have the idea here of what interference is, as you recall. I'm glad you do. Is that you have 2 waves, and if they're out of step, in other words, if you have another wave which is coming in just out of step with it, out of what we call out of phase, you get the sum of wave A plus wave B, and if they're out of phase, they can cancel this plus this to equal 0. So this is a unique feature of waves. And later on, we're going to see that we have even material things in quantum mechanics. The key idea of quantum mechanics turned out to be that matter is a wave. And this bothers people to this day. How can you take one particle and add another particle and get no particles? See, that's the puzzle of quantum mechanics. And if it's a wave, it should do that. And in fact, it does. It's weird, but we have that nature. So this isn't the interference effect. We have the idea that the wave, there are some other ideas that come with it, like coherence. In other words, the wave might not be of infinite length. It might just die out. So if these 2 things are going to interfere, they have to match over their length of existence. So sort of a coherence length over which this is a wave. Now, if we make the wave artificially, so that's the story that I try to tell here, you have to have the coherence of the waves. If we make the waves artificially, we can make the coherence length infinite. In other words, this is a sine generator. Have you used this yet in class? This just creates a sine wave, this little box. These are speakers. So this is going to create a sound wave. I can adjust the frequency. Here it's 688, 600 cycles. That's within the audible range. We hear from about 50 to 10,000 cycles. So 600 cycles is audible. You'll hear it. So I'm sending 680 cycles. That's that. Oh, what do we tune instruments? 440. You want to hear 440 just for fun? Isn't that what the oboe tunes the orchestra for? Does anybody know? Is there a musician in the house? 440? Ooh. Oh, it's an A? Okay. So everybody tuned to that? Okay. Tune your ears. I wonder if we could work with 440. Well, the idea is that, let's try. Now, the sounds are coming out of both of these speakers, and right now, is there any, let me tune this. Does it get louder or softer? How about you raise your hand if it's soft? Everybody's hearing soft. That's kind of funny. I was hoping it would be some more directional. Now, I hear it loud myself. I would have thought that it makes a difference between, because you see the sound is coming from here, and so the two waves are adding up at my place. And I would think that when the distance is just a half a wavelength, they would be canceling. I hear it soft. Everybody hears it soft. You hearing it loud? But I hear it soft for some reason. Do you hear it? Mezzo, soft. I hear it loud. What do you hear? Soft? Loud? Soft. So they're soft, we're loud. I'm loud. That must be about half a wavelength. No, it must be adding constructively in order that I hear it. Okay, so I hear it pretty loud. Anybody hear it soft? Over there. Okay, so that what's happening is that for these people, the waves are coming different distances, but they've come back in step. Even though they're different distances, they've come back. So they start out differently, but somehow they get into step, even though they've come the speaker is so on like that. So that's the key thing is a path difference. That's the whole thing works on path difference. Now, how you create a path difference is, one way is this way, where you see there's a path difference between here and over there, because one is starting here and one is starting here. Or you could put some material in there, which would slow one beam down. Or, well, dream up something. Yeah, or you could put a mirror or something to do it. So that's the main drift of this idea. And that's what it is. Now, we have 5 minutes. The waves here, obviously, are sound waves. This is it's a speaker, and it's driving the speaker at whatever. What do we get, 440? 440. Okay, that was sound. That's a compressional wave. Now, we'll show you another one of our types of waves is these microwaves, of which this is an example. You remember that we've used this before. This tube here creates waves whose wavelength is about 2 inches, maybe an inch, something about like that. And it comes out of a pipe. So there's an electromagnetic wave coming out. This is the microwaves that are in your cell phones, your microwave ovens, and so on. And what's in here is just little steel balls. In every one of those holes, there's a steel ball. And they're just piled in a stack like this, which is supposed to represent a crystal, atoms in an array. Or this could have been DNA, but DNA is a much more complicated story. How Watson and Crick looked at that picture and said, aha, double helix. You had to know a lot more than this. But this is a pretty simple structure. And let's see. Is this one on? This one? Okay, now that one's on too, I trust. Okay. Now, so what's happening, the microwaves are coming toward this array of periodic structure. Okay, so now the tube is warmed up, and there's electromagnetic waves coming through here. They reflect off this periodic structure, and because some of the waves reflect off a ball over here, and some of the waves reflect off a ball over here, they have different path lengths when they arrive back at this horn to be captured. So you get a path difference. If the wave's path difference is a half wavelength, they're out of step, they cancel. So that's what you get in a diffraction pattern. You get, as I rotate the angle, it goes away because they're canceling. It's noisy, squeaky, isn't it? That's not me. That's this thing. It could be me squeaking. So here, somehow the reflection off the balls is coming in such a way that the waves are coming back in step, and you get a peak. And then the reflection off the balls is coming back out of step, and you're getting a minimum. So it's sort of like what we were doing with this. Difference is just to show the point that we are dealing with waves, and every wave, characteristic of waves, and you can prove it's a wave if you get this interference effect. And then, of course, came quantum mechanics and said, my God, you can even do that with particles. We'll get to that. But here's a minimum, and here's a maximum. And so, this someday in your career, you may actually ask some crystallographer to measure the wavelength. And the trick is, notice that the interference effect occurs, as I said, when the wavelength is roughly the size of the interfering object. I said the wavelength is about an inch. You see these separations here are about that wavelength. And again, the wavelength of sound, that's an interesting point. Let's calculate, just for fun, or serious fun, the wavelength of that sound wave. Do I have that up there? See, the wavelength wants to be similar to the periodicity of the lattice. This is another characteristic thing. The velocity of sound in air, I looked it up, is 344 meters per second. So how do we calculate the wavelength of that? The frequency we set at 440. So does anyone remember the formula of the velocity is equal to the frequency times the wavelength, so that the wavelength is equal to the velocity over the frequency. So that would be 344 meters per second over the frequency, 440 per second, or hertz. Anyone want to do a quick number here? That's like 34 is 17 over 22. That's roughly, 0.8 meter. So the wavelength is around an eighth of a meter. This is about 1 meter. So the wavelength here is similar in size. One way of remembering this very obvious thing is that suppose you were on a ship, what size wavelength would bother you the most? What? The length of the ship. Yeah. Because if the wavelength is very long, it's a swell, you're not bothered much. If the waves are very short, it doesn't bother you either. What bothers you is this. And on that note, making you seasick, we can stop for the day. Thank you.